Welcome to topic 5.9, where we're going to start looking at some of the trends in which we have in the periodic table. When we look at our modern periodic table arranged by increasing atomic number, we find that there are other patterns that emerge. And two patterns we're going to look at today is the pattern of atomic radius and ionic radius. So you're going to need these notes. Periodic table and a couple of highlighters might also be useful depending on your preference. And so we're going to look again at how these are arranged with the periodic table. So to start out, to define atomic radius is essentially working towards finding the size of the atom. So you probably recognize the word radius from geometry. So we're looking at half the distance. And so we can measure the distance from one nucleus to another and divide that in half to get radius. So again, what we really care about is we're just essentially looking at how large is the individual atom for different elements. So when we look at a trend, we have to look at it two ways. And so we're going to talk about how a pattern works within a group or a family. Remember, groups or families are these vertical groups. We have 18 of them. And then we're going to talk about it across a period, which are these horizontal rows. We have 7 rows to the periodic table, so 7 periods. So we're going to first talk about what happens to the size of the atom as we move down the group. And so for that, the first thing you have to recognize is the number of shells. So shells are the energy levels 1 through 7, or like the rings on the Bohr model. So as you move down a group, those number of shells are going to increase. And the next thing then is, if you think about it, as the number of shells increases, we have what's called nuclear shielding taking place. What I mean by nuclear shielding is essentially those electrons in between the outermost energy levels. So say you're talking about potassium, which has 4 energy levels. That means there are 3 energy levels between the nucleus and those valence electrons. So essentially those 3 other energy levels are kind of forming a barrier to keep those protons from having an attraction towards those valence electrons. So the more energy levels you have, the more shielding takes place. And so that means that is going to increase. We have more shielding taking place. So because that shielding is occurring, attraction is going to go down, meaning the attraction of the protons in the nucleus to those outermost valence electrons. So because there's less of a pull of those protons on those electrons, the size of the atom gets larger. So that means as you move down a family, the overall size of the atom increases. When you look at moving across a period, so as you go, typically we are looking at it going from left to right. If you think about it, if we look at not family, but period 3, the 3rd row here, all of these have their electrons stored in the 3rd energy level. So as we go from sodium to argon, all those electrons are staying at essentially the same distance from the nucleus. But the one thing that changes, we go from left to right, is the number of protons is increasing. So protons increase as we move across, and so the nuclear charge, so the overall basically number of protons in the nucleus, is increasing. Those valence electrons are going to get closer to that nucleus, and so the attraction increases. Those protons have more of a pull on those electrons as we make our way across. And so what happens is the size therefore gets smaller. So again, what we look at to essentially determine the size of the atom is if you're adding more energy levels, the size will get bigger because the protons cannot pull on those electrons. Versus as you go across to the right, you are not moving those electrons further out, and those protons are being added consecutively. Therefore, that's going to make the overall atomic size decrease. And so atomic radius, is it going to increase or decrease down a group? It's going to increase, so the size gets larger as you move down. And then as you go across a period, it's going to decrease. So the atom gets smaller as you go from left to right. So an atom or an element that's at the bottom, so it's meaning at the bottom of a group, so francium compared to, say, hydrogen, is going to be larger because it has more energy levels to create that nuclear shielding, which makes the overall size increase. So an element that's going to be to the right is going to have a smaller radius than an element to the left, because if you move one spot to the right, it has gone up by one proton. Electrons are in the same distance from, because it's in the same energy level, so that's going to pull those electrons in more, decreasing the size. So the last thing we're going to do is this box here on your notes is just for us to draw the overall trend. So the overall trend for atomic radius is that it increases as you go to the left and it increases as you go down. So this is where you're going to find something that's large versus small. And so francium is in the bottom left corner. That's going to be the largest element compared to helium, which is in the upper right corner. So the last thing is, with every trend, we're going to talk about, does it include or not include family 18 or the noble gases? Because depending on what the pattern is showing or doing for those elements, sometimes the noble gases follow that rule and sometimes they don't. So when we describe and discuss atomic radius, we can include the noble gases. And the reason why is pretty simple. Noble gases, they're an element, they have atoms. And so they have atomic radius. So we can describe the size of the atom and make comparisons, including the noble gases, for this particular trend. The other trend we're going to look at today is ionic radius, which not much of this changes in terms of the trend we just discussed. And so ionic radius is still looking at the size of the atom. The part that's different here is we are now looking at it in terms of an ion. So the same idea, we're going to discuss it from the two directions as we move down a group and as we move across left to right. So as we go from the top of the periodic table to the bottom, just like atomic radius, our shells increase. We have more energy levels moving down. So that means nuclear shielding is also going to increase. Again, that shielding effect is essentially telling us that those electrons are getting further out from the nucleus, and those kind of barrier electrons, those electrons found between the nucleus and the valence electron shell, provides that shielding for those electrons to not have that attraction. So attraction is going to go down, so that means the size will increase. As we go left to right, just like before, protons moves up. So shielding isn't going to do anything here because we're not adding energy levels. Those electrons are being added to the same energy level. So what's changing here is the nuclear charge going up, meaning more protons or more positive being condensed into that nucleus. So that means the valence electrons move closer. Attraction is going to increase because you have more protons to pull on those electrons. So the overall size is going to decrease. So again, just like we discussed in topic 5.8, remember we have two types of ions. So metals, overall, those are the ones found in families 1, 2, and 13 to the left of the periodic table. They like to lose electrons because they have 1, 2, or 3 valence electrons typically. So it's easier in their scenario to lose electrons to get to that octet versus gaining to get to their octet. So when they lose those electrons, they form a cation. And that's because, well, let me backtrack. I'm losing my train of thought here. So they form cations, and the reason with size then and how that ties in is they are losing outermost or valence shell. So overall, they become smaller and size decreases. So here we have a neutral magnesium. This is 130 picometers in radius. And we can see after it's lost 2 electrons, the overall size decreases, which it should make sense. If it's getting rid of something, that means those outermost valence electrons are gone. And so there's less nuclear shielding and those atomic radii get smaller. On the flip side, nonmetals, remember these guys like to gain electrons because they typically have 4, 5, 6, or 7 valence electrons, so it's easier to gain to fill those electrons, and we call those anions. And again, it's electrons are going to now repel in outermost shell. So what I mean by that is that we have more electrons being added to that valence shell. And the more electrons we have in that valence shell means we have more negative charges, and like charges like to repel. So some repulsion effects are happening in that valence shell. And so that means that it's going to get larger, therefore size increases. So here we have a neutral fluorine. Here we have a fluorine anion that's gained 1 electron. We see that the radius is getting larger because it took in that extra electron. More repulsion is happening there, and that's going to increase the size of that nucleus, or not nucleus, but the overall atom or ion size. So looking at this overall trend and summarizing it, ionic radius is going to increase as you go down a group, and it's going to decrease across a period. So in terms of overall size of what's happening, again, if we were looking at all ions and all of them are charged, that trend still follows atomic radius. So elements at the bottom are still larger. Elements at the right are smaller. And so in general, anions tend to be bigger, though, than cations. And so when we look at ionic radius in terms of the overall trend, it follows the same as atomic radius. We can abbreviate this IR for ionic radius. So the last thing that I have is, before that, is if we can discuss ionic radius of noble gases. Well, if we remember, noble gases are full, they're not going to gain or lose electrons, therefore they're not going to form ions. So when we discuss ionic radius, it does not include the noble gases, and it's because they do not form ions. And that means they do not have an ionic radius then. So the last thing that I have for you is I realized I didn't put any practice problems that mimic what you will see in your homework assignment. So if you want to take a moment to pause this, you can add it to the backside of your notes, jot it down in a piece of paper, but work these few examples out. It'll help make your homework go a little bit easier. So the first problem I'm going to do is this one in the upper left-hand corner, and that will kind of help you with these first 2 problems on the homework. So it asks, which has the largest radius, Na, Cl, or Cs? So to do this, you need a periodic table, and you're going to find all 3 of these. And it's asking for largest here. So you identify your 3 elements. So we have sodium here, chlorine here, and cesium here. The overall trend for atomic radius, again, is it gets larger as you move to the left and down. So whichever element is furthest to the left and furthest down will be your largest. And it's, in this scenario, that makes cesium our largest atom. The next thing is going to do the rank part, and that's what's going to help you with this middle section of your homework here. They want us to rank in order of increasing atomic radius. So we have more elements to work with compared to this one. So how it wants you to do this, and that's going to help you with this part here, is it's asking elements on the radius trend. So what it's basically asking you to do is put these set up in a format that's organizing them like they are on the periodic table. So the first element we have is lithium. And so what I'm going to do is place these in relationship to lithium. So rubidium, if you find rubidium, is found beneath lithium. So I'm going to list that below. If you take a look, boron is to the right of lithium. So I'm going to list that here. And carbon is found directly to the right of boron. Francium, if you find it, it's found both below lithium and rubidium. So I'm going to place that here in the bottom left. And then the last one is neon, which is to the right of both boron and carbon. So all that's done is given me, it's basically organized these to help arrange it. So now for my final answer, it wants me to go in increasing atomic radius, so from small to large. The element to the far right is going to be our smallest. the one in the far bottom left will be the largest. So to go in increasing, that means neon's the smallest, carbon, boron, lithium, rubidium, followed by francium. So the last two problems are essentially the same idea, just working with ionic. In this next problem I have set up, it asks what is the smallest, or which of the following has the smallest ionic radius. We have magnesium with a +2, radium with a +2, and calcium with a +2. So we have magnesium here, calcium, and then radium. It's asking which one is the smallest. So at the top of the family is going to be your smallest ion. Of those three, magnesium is above the other two. That makes magnesium the smallest. We're going to also rank this in order of decreasing radius, so from large to small. So same idea, kind of place them like they're on a periodic table. So I'm going to go ahead and write out K plus 1 and then arrange the remaining 3 around it. So we have aluminum. I'm going to also just take care of like charges because those are going to be what's closest. So K, so right above potassium would be the sodium. And if I look, magnesium is directly to the right of sodium and aluminum is just across the way. So again, like up here, I've just arranged them kind of like they're on a periodic table to help with my arrangement. So we need to start with our largest atom first because it wants decreasing, so large to small. So bottom left is going to be where I need to start. So potassium is going to be the largest, followed by sodium, magnesium, and that puts aluminum as having the smallest size compared to the other 3 given in this group. So that's essentially what you're going to do on your homework. If you have any questions or need any extra help, please feel free to reach out to me.